Gauss's law continued. So we've done the region from r equals 0 to r equals a. Now we're interested in the region from r equals a to r equals b. And I'm going to go ahead and draw in there a Gaussian surface. I'm going to use a thick black line to do that. And I'll pick some arbitrary radius. And so my dashed line there is my Gaussian surface. And let's take a look at what Gauss's law gives us. The integral over some closed surface of E dot dA is the charge inside of that closed surface over epsilon naught. So again, I already talked about the fact that we have spherical symmetry. So this integral becomes the integral of E and dA, and E is constant, and the integral of dA is just the area. So the electric field times the area is Q in over epsilon naught. The area, surface area of a sphere is 4 pi r squared. So I'll bring that to the other side and move some things around a little bit. Okay. And what does that look like? That's exactly the same as the electric field from a point charge. We have to figure out what Q in is. In this case, Q in is the entire charge on that sphere, right? Because the entire sphere is enclosed by our Gaussian surface. That's just Q1. Since it's positive charge, the electric field would be pointing outward, or the r hat direction. So there's my electric field between regions A and B. It drops off as 1 over r squared. So I'm going to scooch down here to my plot and go ahead and put it in. Between A and B, it drops off as 1 over r squared. Looks something like that. Okay, so we'll continue along here. If you want to pause at any time, try the next region yourself. Go ahead and do that. I'm ready to go ahead and do the region between B and C. These are less than signs. So R greater than B but less than C. So now we are going to be in this green area on our chart here. And I'll draw a Gaussian surface in there. And again, integral E dot dA is Q in over epsilon naught. That's Gauss's law. But we know something about this region. We are inside of a conductor here, right? And if we're inside a conductor, what does that mean? E has to be 0 everywhere inside that conductor. So we don't really need to use Gauss's law in this case. We know inside that conductor E has to be 0, and that's our answer. I can go down and plot that. Between B and C, our electric field goes to 0. Okay, so there's one more thing we can jump to now. It makes sense to do it right now. We were also asked to find on each one of these surfaces, on the outer surface of the outer shell and the inner surface of the outer shell, and on the outer surface of the inner shell and the inner surface of the inner shell, on those 4 surfaces, what's the total charge on those surfaces? And so we're going to do this shell right now. We know the electric field is 0. We know Gauss's law is the integral of E dot dA equals Q in over epsilon naught. So what does that tell us? if E is 0, that tells us that 0 equals Q in over epsilon naught. And that tells us that Q in has to be 0. So normally we use Gauss's law to find the electric field knowing Q in. This time we knew the electric field, we plugged it in, and we solved for Q inside our Gaussian surface. So let me go back and look at our drawing one more time. And if our Gaussian surface, I'll use red. If our Gaussian surface is here, then the charge inside of that red dashed circle has to be 0. And we know that on the innermost circle we have positive Q1. And so we have to have negative Q1 somewhere else inside of our red dashed circle here, inside of our new Gaussian circle, because the net charge has to be 0 inside of this red Gaussian surface. We're not interested in this one anymore. We're interested in the new one, the red one, because we're at the new region now. So inside of this red dashed Gaussian surface, our net charge has to be 0. We know the blue area has a positive Q1, so there has to be a negative Q1 somewhere in there. Well, where else could it be? It can't be, there's empty space between A and B. It can't be in there. It can't be inside of our conductor. It can't have charge inside of a conductor. It has to be on the surface of a conductor. So it has to be on this inner surface. So the total charge on the inner surface of this conductive shell, that's where R equals B, that has to be negative Q1, because the charge, the total charge inside of our Gaussian has to be 0. So the Q at R equals B, it has to equal minus Q1. So if Q1 was given, it was as positive 6 microcoulombs, then at R equals B, we would have to have negative 6 microcoulombs of charge. And what would the charge be at Q equals, what would the charge be on the surface where R equals C? Well, let's take a look. We know the net charge on the conductive shell, the innermost conductive shell, is equal to negative 10 microcoulombs. That was given in the problem. The net charge on this conductive shell is negative 10. And we know negative 6 of that went to the inner surface. So what's left over? That has to be on the outer surface. So we know the Q on the inner surface plus the Q on the outer surface has to equal the net charge on our conductor. And so if negative 6 microcoulombs is on the inner surface and our total is negative 10, then our outer surface, which is R equals C, has to have negative 4 microcoulombs. Okay, I think I'm going to pause the video again here and pick up with the next region in a new video. And in the meantime, you can give it a try and maybe you won't need the video.